So it's a brief outline of my talk, and I will first talk about alternatives to black holes and why to look for them. Then I will talk about how to probe quantum effects of black holes through gravitational waves, a few observables and implications, and then what are the directions to look forward. So I've just listed, the most recent works which I will present. I will mostly present the first and the third one here. But there are others in the process. So, okay. So let us start with the fundamental question that why black holes are important. And there are, more than half a dozen reasons you can write down for it. So I've just listed according to my own preference. So first of all, black holes can be constructed out of normal matter. You can have a nice and simple collapse scenario from which you can construct a black hole, and which I don't think exists in a more generic sense for other, like any exotic compact object or wormholes and things like that. Then, of course, they're unique and have universal property, which we have heard today morning from Vitor. So, if you have mass and charge, then Reiser-Nostrom is the only solution to GR. You have the similar situation in the case of a curved black hole, and so on and so forth. Then, of course, when we talk about black holes, we obviously graze through the thermodynamic properties that black holes have, like it has a temperature, it has an entropy, and you always go towards that direction to talk about any connection of black hole with quantum gravity and those related aspects. Then, of course, another important feature is that black holes are stable under all possible perturbations that we have. We have the quasi-normal modes, and perturbation indeed decays with time. But of course, as Vitor also mentioned, if you add perturbations to the black hole potential, it is not clear because the quasi-normal modes drift away, and what happens to the stability is, I think, is an open problem to understand. And we, of course, have observations from the LIGO-Virgo collaboration, as well as observation of black hole shadow, and all of those put together consistent theory of black holes in general relativity. And if you talk about whether it is consistent with GR, that, as I say, it's a different story. We'll just talk about black holes here. But there are issues, some of which have already been discussed. So there are three main issues which I listed. First is, of course, the existence of singularity, and that is something which is definitely a problem because your theory breaks down at a certain point, and that is something you definitely want to avoid at all costs. And then there is loss of predictability, which comes from the existence of Cauchy horizon. So most of the black holes, astrophysical black holes, for example, they have Cauchy horizon. And if you put them in a de Sitter background, which of course we live in, then the regularity at the Cauchy horizon is not always guaranteed. And in particular, you cannot probe beyond the Cauchy horizon, because that's where, if you give an initial data, you cannot predict what is going to happen beyond the Cauchy horizon. And that precisely can be questioned in the case of a de Sitter background. And that Vitor showed in 2018. So people have worked on it further. So for example, Bob Wald came with a solution where he argued that if you include quantum effects, in particular quantum fields in the background, that can possibly cure this problem. So you can see there are many mixtures, quantum classical intermixing to solve these issues. Then, of course, the long-standing puzzle of information loss paradox. So what happened to the thermal radiation that comes out of the black hole? What is the end stage of it? How do you gain back what you have thrown into the black hole? So for example, if you don't like your colleague, you can throw him or her into the black hole and get rid of it as of now. But maybe 10 years down the line, when you have a resolution to this paradox, you may be able to retrieve information and the police can catch you. So all of this suggests that you look for alternatives which can cure this problem, and yet it has to remain consistent with experiment. So with this, you come back to this black hole hypothesis, which I think Cardoso and Pani presented. So the idea is that does existence of a photon sphere implies the existence of a black hole, in particular existence of an event horizon. So what we have seen, both from the quasi-normal mode spectrum or the ring down spectrum in LIGO-Virgo, as well as from the shadow measurement, are just the photon sphere. And I think Vitor emphasized it several times in his talk that we actually have not seen anything which is beyond the photon sphere. So if you do a simple WKB calculation, you will find that the photon sphere or the modes associated with the maxima of the potential is very well, it mimics the quasi-normal modes of black hole. So you really do not have to go to the horizon to talk about the existence of a ring down. And similarly, the photon sphere, as you can expect from the shadow measurement, it only relates to the properties of the photon sphere. So you really have not probed inside the photon sphere. So the question is, can such objects exist, and what are the observational verifications of this? Objects whose radius is smaller than the photon sphere, but larger than that of the black hole. So that's what brings us to the one of the main contender in this direction, which corresponds to the exotic matter scenario. So often people argue that if you have normal matter and it starts to collapse, then we have Raychaudhuri's equation, and which guarantees that it is going to collapse and form a black hole at some level. Unless, of course, you include some exotic matter or some quantum effects, then you can halt the collapse at some level and you may not form black hole at all. So effectively, what you need for consistency of observation is some star, some material, some object whose radius is between 2m and 3m, if you talk about Schwarzschild. And that people have already achieved. I think yesterday, Rami talked about this Bugdal sphere. This is the most compact, stable stellar structure that you can construct. And that radius falls to 4/9, which is smaller than 3m, but it's larger than 2m. So therefore, you can ask that, well, it's pretty good. So you can have a star which is of the order of 4/9. So it does not have to violate any energy condition. It can stay put there. And what we see would match exactly with the observation and from that sort of a star. But again, the recent shadow measurement, like from the Sagittarius A star, argues that it is not really the case. Because if there is a star whose radius is of the order of Bugdal star or even smaller, there should be outflows from the surface of the star, and that should actually enhance the temperature that they have seen on the photon sphere, and which is, of course, they have not seen any such outflow. And from that, they argued that Bugdal limit must be violated if you want to have a star which is more compact than that of the photon sphere. And if you violate the Bugdal limit, there is no way you can construct a star with normal matter whose radius is larger than that of the event horizon. So you need exotic matter into account. But again, just like black holes have their issues, I guess exotic matter have their own exotic issues. So this stability of this exotic matter is, of course, a serious trouble. So if you have rotation, it sort of exaggerates in the sense that you have ergo region instability, you have enhanced superradiant instability. So for black hole, superradiant instability is often tamed because the black hole absorbs everything. So therefore, the growth of the power, the growth in energy is not all very large. But if you have a reflective surface like a star or whatever it is, then it's not going to be absorbed. So therefore, the energy can build up inside your ergo region, and that can in some sense lead to runaway instability. So that brings us to the topic which I'm going to discuss, is that can quantum effects play any role? So if I remember correctly, this was Niyesh Afshordi and his students who first pointed it out in 2017. And after that, there were several papers which discusses this effect. And one of the most important one was very recently in 2021 by Ivan Agullo et al., where they discussed the case of area quantized black hole. So this area quantized black hole appears in various contexts, in particular in loop quantum gravity, and they have very non-trivial physics at the horizon. For example, this area quantized black hole argues that it only absorbs the radiation, whatever falls into it, at a very definite frequencies and reflects all the others. And all of this actually comes down to a single umbrella, that is, you modify the horizon by a reflective membrane. And this reflectivity is what captures the interior structure of this material. Whether it's a boson star, a area quantized black hole, or something very different, these are all captured by reflectivity. So if by any means you can actually see whether that object has a reflectivity, that's the first thing that will tell you that it's not a black hole. And second, if you can identify what is the behavior of this reflectivity, like how it varies with frequency, how it varies with rotation, and so on and so forth, that will give you an idea that what actually is the nature of this object. Is it quantum, or is it just some star made out of an exotic matter? So as I said, the basic point is to modify the horizon itself as a reflective membrane. This is just a cartoon of what is going on here. So in the context of a black hole, you have the so in the context of a black hole, you have just, I mean, there is the angular momentum barrier or the photon sphere. So a part in the QNM analysis goes towards infinity and a part goes inside the horizon, and that's it. That's the boundary condition. But on the other hand, if you put some non-black hole nature, some membrane, some quantum feature, some exotic matter, then along with a part which goes inside, there is also a part which comes out of the black hole. And this R corresponds to the reflectivity, and that's what one wants to determine. So what I will discuss, we always mention that, I mean, the horizon of a black hole is a one-way membrane. So I will just try to sort of, modify. So it will follow mostly this paper by Elisa in 2020, and the idea goes back to the dates of Price and Thorne. So what you have, instead of a black hole, you replace it with a membrane, and you ascribe the membrane some properties, like it will have some shear viscosity coefficient eta, some bulk viscosity coefficient zeta, and there would be some energy density rho and some pressure P. So if you prescribe these numbers, you have prescribed the corresponding object which is inside. So for example, for black holes, this eta would be 1/8 pi, and this zeta would be minus 1/16 pi. So some very specific numbers for these objects. And suppose observation tells you that this eta is not equal to 1/8 pi, or zeta is not equal to minus 1/16 pi, that would be a clear signature that we are not really looking at a black hole. And then what you do, you study perturbation of the background spacetime, and the corresponding matter field will also be perturbed, and that is done through this junction condition. So you can see whenever you are perturbing delta TAB, which is the fluid which is living on the membrane, you are perturbing it. That in turn is perturbing the KB, and this KB is coming from the geometry which is outside, because you have to match these two things at the surface. And when you do that, you end up getting this boundary condition. As you can see, since the membrane is fluctuating, it cannot be at the location of the horizon. So therefore, you have this extra piece over here, and this V axial is your Regge-Wheeler. And if you do it for the case of Zerilli, you will get a similar boundary condition. So if your R is really at the horizon, your V axial would be 0. And therefore, you will only be left with this equation, which, as you know, it has a plane wave solution. And if you do it, even keeping all of it into account, I mean, you will get the reflectivity to be related to eta over eta black hole. So then you see, if your eta is same as that of eta black hole, then this is 0, and that's what you expect. Nothing comes out of a black hole. And if your eta is not equal to eta black hole, there would be, reflectivity which would be non-zero, and something would come out. So this analysis was done in a classical setting. So what we did is sort of to assume the membrane to have made out of, harmonic oscillators in its ground state. Because in physics, harmonic oscillator is the, only problem that we can beaten to death. I mean, we can solve it to as many precision as we want. So therefore, you take a large number of harmonic oscillator in the ground state so that your wave function would have something like a Gaussian structure. And then, you can compute where the classically it would be located at the expectation value, what would be the corresponding dispersion relation, like what would be the fluctuations present. And the classical limit would simply corresponds to the sigma tending to 0, which will give you back your good old black hole scenario. And you can also do it with the energy momentum tensor. You just include them into operators. And you may try to ask what happens to the junction conditions at this instant. That is simply taken care of by the way you do semi-classical Einstein's equation. That is, instead of taking TAB, you just take expectation value of TAB. I mean, that's as simple as that. Yes, yes, yes. We do not know. So for the interior, we're just setting that there is KB and K. These are all 0. It's just the exterior KB and K which you match to TAB. Yes, yes. And pardon me, I do not know. So I just have a TAB on the membrane. So the idea is that you do not care about what is inside. Whatever is inside, it is embedded on the membrane with its eta, zeta, rho, and p. And that's all that should matter to you as an external observer. No, the KB, the extrinsic curvature is 0 inside, but it is not 0 outside. So the difference is due to the existence of a TAB, which is the membrane. So
assuming KB is between 0 inside, sufficient to go to the equation. Then if you choose some other inside, you will have a different picture.
Exactly. Okay. And as in the previous case, here also you have delta KB and K delta HAB, because it turns out delta K is actually 0 for this context, is related to delta of TAB. Exactly in the similar manner as in the previous case, but with some, these quantum fluctuations taken into account. And then what we did is just to do it for the case of axial. I mean, you can do it for the polar as well, but it just get a bit more complicated. And you can see it is the full boundary condition, and it is different from what you would get from the classical case. There would be these extra pieces which appears in this context. And you can easily see if you take the limit capital R, which is the, the surface of this, the average of the fluctuation. If you take R to R plus, then your F is identically 0, because by definition of the horizon, the potential also vanishes at that point. And this term is also 0. So you are only left with the d psi dr term, and this x is the tortoise coordinate with psi. And that is precisely what is required for you to define an perfectly ingoing boundary condition. So you get back as you wish your purely ingoing wave at the horizon when you take the limit of R tending to R plus. So now let us just give some plots. So this is how the reflectivity varies with the frequency omega arising from the boundary condition for different choices of the viscosity parameter eta. So you can see when eta is same as that of eta black hole, the reflectivity is pretty small. I mean, in general, if you are looking at, LIGO type of frequencies, you would be looking at somewhere here, 0.11, which is omega m. So here you can see the reflectivity is of the order of 10 to the minus 7 or so. But on the other hand, if your eta is large, say for example, this red one, then your reflectivity is always pretty close to the value of 1. So that means depending on eta, your reflectivity can vary very differently. And if you are not really looking at a black hole, it would be very different from what you would expect. And it also depends on how close this surface is to that of your would-be horizon. So if it is small, your reflectivity is small. If it is large, your reflectivity is also larger. So these are the features that we also expect in the normal context. And if you simply expand, you can see that when the sigma is 0, as it was in the case of a classical membrane, then you simply retrieve this result of 1 minus eta over eta black hole as expected. And following your expectation, the ring down, the time domain waveform will definitely have echoes in it. So here itself, it is evident. So you can see that for eta 0.01, which is very different from that of a black hole, you have 3 repetitive pattern which is present. If you increase the value of eta closer to that of eta black hole, the amplitude sort of gets decreased. And when eta is very close to eta black hole, you could only discern one of the peak, but all the others are really absent over there. And for different choices of sigma also, the same repetitive feature is present, but it's just that discerning them becomes different. And you can also probe the time delay out of this analysis. So for example, the difference between the two would be related to log of this sigma, for example. So you can see when sigma is larger, when sigma is smaller, log of sigma would be larger. So the time delay would also be larger and vice versa. And so similarly, when you do it for the case of a very large value of sigma, that means you are changing the horizon by a large extent. Even at very early time, you can see differences which is dropping. And another feature that we observed, but we could not give a very good explanation, was that what we found is that, after some time, the signal was getting flattened out at later time. So it was not very clear. It was very akin to that of a memory effect, because in memory effect also the signal gets flattened at a later time instead of decaying as a power law. but there was no reason why such a memory effect would arise, and we did not pursue it further. But these features were present in the time domain analysis. So whether this is the Regge-Wheeler. So yeah, so whether it's an artifact of the numerical simulation or whether it's some real thing is an open question, and one can possibly study. So this sort of finishes the first part, which discusses the ring down phase of the analysis. So let us now go to the in-spiral part of the analysis. And in the in-spiral part, there are two main phenomena which one can address. One is the tidal love number, and the other one is the tidal heating or tidal dissipation. Now, tidal heating is most important when you have rotation, but we do not have a rotational generalization of the membrane paradigm as of yet. Which we're planning to work for last 1 year. So I will just discuss the case of a tidal love number, and which is another smoking gun test of general relativity, because for GR black holes, as today morning we heard a lot of times, that they have a zero tidal love number. So therefore, if you can get some non-zero value, you know, these things can be tested pretty well. But first thing is that the way it is defined, like starting from the original paper by Hinderer in 2008, the love numbers have ambiguities. And this is mostly because the love number calculation goes from the, the linear, the Newtonian approximation. So what you take, you think of G00 as something like 1 plus 2 phi, you expand it 1 over c, the speed of light order. And then you have a part which goes like, r square, which is the external tidal field. And there is a quadrupolar deformation, which goes like 1 over r cube. And the coefficient between the two is what determines for you the tidal love number. But this definition has ambiguities. And this was pointed out by Sam Gralla in 2018. So the idea is that you have, in a relativistic context, you have coordinate freedom. You can choose any coordinate that you use. You should not just stick to the standard radial coordinate of Schwarzschild. In particular, he gave a nice transformation. He said, instead of r, let us use r prime and see what happens. And what he found is that your Qij is changed. So what is your induced quadrupole moment gets modified, which you can anticipate from this result over here, because it has a higher powers of r, therefore your Qij will get contributions starting from Eij as well. And that's what you see, and you see this n is coming from the n over there. And as a consequence, the love number also gets modified. Instead of lambda, you have changed it by n. So therefore, you have to be very careful when you are saying love number is 0, because it is somehow tied to a coordinate frame or reference frame. So if you go to a different reference frame, maybe you get a non-zero result. So it would be nice to go for a gauge invariant approach to this tidal love number. And that is precisely what has been achieved recently by Latiek, Casals, and Shia. And what he did is, you just solve the Teukolsky equation. And Teukolsky scalars are definitely gauge invariant and coordinate invariant quantities. And you use them to get the tidal love number. So first, what you do, you consider a Newtonian limit of your metric. So you can take GTT to be 1 plus 2 phi by c square and GRR to be 1 minus 2 phi by c square. Plug it in, calculate the corresponding wild scalar, psi 4 or psi 0. And you take ultimately the limit c tending to infinity, which would be the Newtonian limit. And you can show that it precisely reduces to what you would expect from your gravitational potential. You have a 2 KLM, and this KLM are your tidal love numbers. Now, what Shia and Latiek did, actually Latiek did it for the zero frequency case and Shia generalized it for arbitrary frequency, is that this is actually a expansion like this. So we have a 2 KLM, which is the the real part of FLM, and that corresponds to your tidal love number. Then you have an imaginary part which corresponds to the tidal dissipation, and it's most likely related to tidal heating, though no one-to-one correspondence exists. And then you can have higher order corrections. And he evaluated it for Kerr black hole, and he has this parameter P plus, which you can see when rotation is 0 is simply proportional to frequency. When rotation is not 0, this is the omega bar, which is omega minus m into angular velocity of the horizon. And this is the result which he gets. So if you take the real part of it, you can see it's purely imaginary, and I is sitting over there. So if you take the real part of this F, you can see it is identically 0, and that's how we argue that curved black hole have a 0 tidal love number, but it has a non-zero tidal dissipation term. So what we tried to do is to work this out for the case of an exotic compact object, which has a non-zero reflectivity. Yeah. And then when we did it, we get an expression like this. So you can see here we have two parameters, this B and A, and there is gamma 1 and gamma 2. So let's not get into gamma 1 and gamma 2, which are complex quantities and have a long expression. But this A corresponds to the ingoing part of your wave, and B corresponds to the outgoing part of your wave at the horizon. So if you have a black hole, then B is 0. There is nothing coming out of the horizon. So you end up getting the result of Shia, and the real part of it is going to be 0 because there is an I sitting out there. But on the other hand, if you have a non-zero value for B, then gamma 1 and gamma 2 are complex, and therefore this is a complex quantity and there is an I, so there would be a non-trivial real part present, and that will give you the non-zero tidal love number for an exotic compact object. Now, how do you define reflectivity? So generally, B by A comes from the Teukolsky's function, but Teukolsky's functions are not well defined on the horizon. You know, you have delta to the power minus 2s minus 1 and factors like that. So what we did, we instead defined it in terms of the Detwiller function, which is perfectly, you know, is a plane waves solutions which exist without any prefactor. And then you can relate Teukolsky to Detwiller using the transformation. And therefore, there would be additional factors coming out there due to this transformation. But after all this, you can get an expression for the KLM, and that is something we are currently working on. So rather than going to that direction in the last 2 or 3 minutes, let me focus on the static part of it. Because already Vitor, Paulo, and others had a paper in 2017 on the love number for exotic compact object, and they got a log epsilon behavior. So if the compact object's radius away from the would-be horizon is of the order of epsilon, then the love number scaled as log epsilon. And so let me see how that result comes about here. So for that, the original results were in terms of metric perturbation, the H0 or capital H0 or small h0. So therefore, you have to go from Detwiller to all of this metric perturbation. So this is done in the following step. You go from Detwiller to Teukolsky, and it turns out Teukolsky function can be written in terms of Regge-Wheeler and Zerilli. There is a closed form expression. And Regge-Wheeler and Zerilli can in turn be related to metric. So all these statements that we can make in terms of the Detwiller function can, at least in the zero rotation case, be transferred to statements on the metric perturbation. So let me go over there. So let us look at this connection between H0, which is the metric perturbation in the axial gauge, and psi Regge-Wheeler is the Regge-Wheeler function. So you see, the condition that was imposed in that 2017 paper was Dirichlet boundary condition. That is, you take psi Regge-Wheeler to be 0. So if you take psi Regge-Wheeler to be 0, it is evident that H0 prime by H0 is simply 2 over R. Because if psi is 0, then it's only the psi prime by psi term which dominates. The F cancels, so it is 2 over R. And we wanted to see how do you get this 2 over R in terms of Detwiller. So for that, we also expanded the reflectivity, which is R0 plus I omega R1 and higher order terms. We started with these ansatz for the Detwiller function. This is the ingoing, and this is the reflectivity times an outgoing. And this would be, you know, the corresponding x prime by x. And that is given by this result. So you can see if your R0 is not minus 1, then this would actually vanish when you take the limit omega tending to 0. Only when R0 is minus 1, this limit would become finite because, you know, things would cancel on the top and bottom. And you can actually get H0 prime by H to be 2 by R for a very specific value of R1. For all other choices of R0 and for all other choices of R1, your H0 prime by H0 will not be 2 over R, and Dirichlet boundary condition would not be satisfied, and you would never get the log epsilon behavior. So in that sense, this log epsilon behavior which was derived was a very specific to a very particular choice of the reflectivity, and it does not hold in general. So I will just skip this part and I will just come to the conclusion. So the models of quantum black hole imposes a reflective nature on the black hole horizon. There are echoes in the ring down signal. And there is a dependence of this reflectivity on the viscosity. And this viscosity parameter is something important because it captures the physics inside that corresponding membrane. So if you have some, quantum gravity motivated model, like often string theory would speak about some value of the viscosity coming from the underlying degrees of freedom, like the eta by S ratio, which is often quoted. And if these are different from that of a GR-like black hole, in principle, this can be tested using gravitational wave observation. That was for the ring down part. The in spiral part also gets affected through the tidal Love number of an exotic compact object. And as I said, it does not scale as log of epsilon in general. And finally, as I said, the rotation needs to be included because otherwise we cannot apply it to real data. And of course, the tidal heating needs to be addressed because that appears at a higher post-Newtonian, higher in the sense that 2.5 pn compared to 5 pn. So maybe it would have a more significant effect on the phasing of GW, and possibly we can extract useful information. So thank you. Thank you very much.
Thank you very much. Massimo?
Is it correct to expect that when the reflectivity is modulus equal to 1, the Tidal Love number is real instead of
Yeah, no. So let me see where it was. Yeah. Not really, because these gammas are complex. So even if you have reflectivity equal to 1, you will have a non-zero Love number.
No. Yeah, non-zero Love
Yes.
numbers are real.
Yeah, real, because Love number is the real part of it.
I think he's asking whether there is also a dissipative component.
Okay, dissipative component.
It's purely imaginary when the easy.
Yes.
Now, if there is any space, there's no nothing that is
We didn't check it yet.
Jordan described yesterday.
I would expect that we didn't check it because
No,
this
that
is
we did not.
also in the rotating.
No,
Yeah.
because you see, the problem is that the reflectivity is always defined in the De-Wheeler transformation. Now, De-Wheeler to Teukolsky, there are several factors of I coming from this transformation. So therefore, one needs to plug those in and check really what happens. So no, that is not real. See, the point. No, but you cannot directly put B by A equal to 1, because as I said, the B by A is coming from the Teukolsky function, but reflectivity is best defined in terms of the De-Wheeler. And this transformation from Teukolsky to De-Wheeler also involves factors of I, which you need to take into account before making any comment. But yeah, I guess we'll check that out. Thank you.
Then
You mentioned that the tidal dissipation is related to tidal heating, but it's not a one-to-one.
One-to-one in the sense that I have not seen a paper which explicitly showed that this is tidal heating. So for example, for Kerr black hole, you know what is this term, you know the imaginary part, and you also know for Kerr black hole what is tidal heating. But whether the factors match, I do not know. I have not seen an expression which explicitly says this is the tidal heating.
Not expecting another effect.
Yeah, I agree, but sure. But in tidal heating, there are other things like, it's not just always proportional to omega bar. There is also terms proportional to the rotation as well. So it's not clear where rotation is because it always comes coupled to omega. So yeah. Yeah, they get this result. I think today itself I was talking to Paolo. They end up getting exactly this expression. But I do not see them doing the tidal heating part explicitly. Okay.
yeah. Other questions? Well, so I have a comment, but maybe this already goes into the discussion session. So at the very beginning of your talk, when you were discussing normal matter versus exotic matter,
there was this issue with Bugdal limit. So I would argue, I mean, Bugdal limit is saturated for a constant density star, meaning infinite speed of sound. So maybe that is already not normal matter. It's sort of a
Yeah, but I mean, I agree. But normally, if you see, for example, Wald's book, I mean, this derivation does not require you to have constant density. You just assume that, you know, your pressure decreases and density also decreases as you go outward. Everything remains finite. So I think constant density is a quick way of arriving at this, but that is not the only way of getting here.
I see. Yeah.
Yes, yes, of course,
Yeah,
of course, of course.
What do you mean?
See, getting this bound for axial symmetry is not possible because interior solution to CAR is not known. So you can only do it for spherical symmetry because you need the exterior, you know, to match and get this M over there. I mean, otherwise you would not be able. So there is no Bugdal bound for a rotating star. I mean, as far as I know.
By the way, one thing that one could do is to take, say, a fluid that saturates causality bound. So the speed of sound is 1, and you will get that the compactness is much smaller than that number.
Yes, yes,
So
yeah. And also if you have anisotropy, because this was done using isotropic condition. So if you introduce anisotropy, you can relax it slightly. Yeah. Yes.
I have also a question, maybe this can be part of the discussion. Each person there is an analog bound for higher dimension.
Yeah, higher dimension in higher curvature gravity. Yeah, there are plenty of them. And
What I have seen, there is something we can discuss. The also Sumanta and also they try to change matter to solve the problem with the cracks. But in theory, but if I'm on natural, it's to go higher dimension. With all these possible solutions and calculations, from the combination of the scales.
yes.
The scalar will be and my question is that
It will change. Yeah, it will. But if you have a scalar satisfying the rho and p, which you know Bugdal used, I think this bound would hold, right? You will take the scalar as a simple fluid model. Oh, you mean in the brain world like scenario? Yes, yes. Yeah, no, that I have not done, but yeah, I mean, yeah, in higher dimension, this can change. Sure, sure. Correct, correct, correct. Yes, yes. Like the Kaluza-Klein decomposition. But I believe as long as in 4D it satisfies the regular boundary and regular condition in the sense, you know, rho does not diverge, p does not diverge. I think this would be pretty.
The trick of the possible solution is exactly that. The scalar field, which near the horizon, the kinetic term will start to be direct.
Yes, but this is not like horizon, right? It's away from it. So I would suspect that here things would be fine.
But by the way, as Sumanta was saying, so this bound in the original proof requires some assumption on the matter. For example, the density has to be a monotonic function of the radius in spherical symmetry, which is based on, say, the expectation that matter should behave normally from the 4D perspective. If you do a compactification, then you may have crazy things and break this hypothesis, and also this is possibility.
And also fastball requires rotation, right? You near extremal configuration.
Now they have some sort of charge in
okay.
Most of them
Yeah, we'll have a talk tomorrow. Yes.
Yeah.
Okay,
So-
so I will say let's thank Sumanta
Thank you.
again. Thank you. So now we have some time for discussion before the coffee break closing today's session. So I will ask everyone if you have comments or questions to the speakers, to today's speakers, or problems or things you want to bring up.